Newton's law of universal gravitation. Newton developed his law of gravity while on a 2-year vacation from the University of Cambridge, sent home to the farm after an outbreak of the Black Plague closed the college. No classes, no professors, no books, nothing but farm chores. Isaac Newton hated farm chores. He spent his couple of years ditching his farm chores, sitting as far away from the farmhouse out in the fields as possible, and thinking. He knew that things fell down and went plop, except for the moon, which seemed not to follow this rule, and Newton tried to figure out how far up does this gravity thing go. After a few years of thinking and working the math, he came to the conclusion that it goes all the way up, that the moon isn't an exception to the law of gravity, but a part of it. Newton modeled gravity as a force between two masses that attracts two masses to each other. Newton thought that every mass attracts every other mass. The force of gravity depends on the size of each masses. Big masses have big forces of gravity, small masses, less such. It also, more importantly, depends on the proximity. Planets that are close to each other have strong gravity. Planets that are far away from each other have much weaker gravitational forces. Newton got this from the astronomical data processed by Johannes Kepler, his Danish predecessor. It stands to reason that by Newton's idea, gravity ought not to affect light rays, they have no mass, time, gravity, time? No, and other massless entities. Newton published his law of gravity in the 1680s. After a very, very successful career. Newton lived alone at this point in a giant farmhouse with a housekeeper whose job was to make sure that he got hot meals and clean shirts. He was the most brilliant mind of many, many generations, and he had an ego to match. He never held regular graduate students at the university. Although he was the head of the department and the head of the Royal Society, nobody ever wanted to work with him because of his big, fat head. He was the most obnoxious, bossy, opinionated person you can manage, and he used to fight like cats with the contemporary physicist Robert Hooke of Hooke's Law and Spring Forces from last semester. Edmund Halley was working out the path of a comet in 1682, and he was certain he could prove it was coming back if only he had a proper formula for the law of gravity. So after many, many, many years of uncharacteristic lack of publishing from someone with an ego as big as Newton, Halley sent him a very polite letter saying, "Sir Isaac, I'm working on this comet problem, and Robert Hooke tells me he's worked out a formula for the law of gravity, and it's just obvious. I asked him to send it to me, but somehow he's never gotten around to it. Now I bet you, Sir Isaac, if I asked you for a law of gravity, you'd have the answer instantly, and you'd be a gentleman enough to answer your correspondence." Bam! Sir Isaac Newton writes back, "If there's something Robert Hooke can't do, by golly, he can. It's the law of gravity. It's the inverse square law with which Halley completes his calculations and predicts that the comet will come back in 1759, long after he's dead and gone. Son of a gun, it does. It comes again and again every 85 years. I saw it in 1986. You'll see it when you're little old ladies and little old men, and it was named Halley's Comet in his honor. The rest of us got the consolation prize, Newton's law of universal gravitation. Newton's law is an inverse square law. The force depends on the distance between the two masses squared. Double the distance, you'll get a quarter of the gravitational force. Let's dissect this formula. The bigger mass goes here, sometimes capital M or M1. This is the mass of the planet or the star. The smaller mass goes here. This is M2, the mass of you or the astronaut or the spaceship or the apple or whatever it is you're dropping. Switch them, it won't make any difference, but why not put the big one first? The distance between them is measured, like all things in physics, from center of mass to center of mass. The cm does not mean centimeters, it means one center of mass here, one center of mass here. Draw the line between the two of them and go. Last but not least, let's check those units. Kilograms times kilograms is kilograms squared. Meters times meters is meters squared. That's kilograms squared per meter squared. That is not the units of force. Newton figured out that we needed one more letter here. He called it capital G, the universal gravitational constant. For one thing, we need a letter to make the units work out. Cancel out the kilograms squared, cancel out the meters squared, and give us newtons. The universal gravitational constant tells us how strong the force of gravity is in the universe. We'll study that in a minute. That actual number came after Newton, who didn't find it anywhere in his century to weigh the planet and check in. Let's make sure we're doing this correctly. What's the distance between you and the ground you're standing on? 0, right? Fine. Distance between you, 0. Plug that in, and oh dear, dividing by 0 can't do that. This is why we have to measure from center of mass to center of mass. When you're doing Newton's law of universal gravitation, always, 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 always start with a diagram. Go on, draw the planet, draw the moon, pause the video, press play when you've got it drawn. This drawing is not optional. Now, draw the center of mass, draw the center of mass, draw the line between them, label it. It's labeled, not optional. Now, what do you need to look up in a data table or on your phone at nasa.gov or perish the thought, the Wikipedia, in order to find RCM for the gravity formula? Break it down. Pause, go from one center of mass to the other center of mass, stopping along the way every time you get something new, label everything. Pause, press play to check your work. There's 1, there's 2, there's 3 pieces. RCM is going to be the distance from the moon to Earth, all well and good, but it also is going to include the radius of the planet and the radius of the moon. Don't stop until you have all 3 pieces. Please note, if you're smaller than a moon, if it's just an apple, the Earth already is more than 6 million meters in radius. 6 million meters plus a couple centimeters of apple is still about 6 million meters. If it's smaller than a moon, we are not going to worry about it so much. Now, let's see what we can do about measuring that universal constant. Universal gravitational constant came with Cavendish in the beginning of the 1700s, one generation later. Cavendish used Newton's law to measure the universal gravitational constant without having to weigh the planet. Newton had already proved that his law was correct, measuring gravitational forces between large bodies in space, showing that one of them was 4 times bigger or one of them was 10 times smaller. Cavendish did one step better. Cavendish took a torsion balance, which is basically 2 of the biggest bowling balls he could find, hung from a system that he designed himself. He made sure that system was isolated, that that balance was completely balanced, except for the gravitational force between the 2 bowling balls. Now, we know the force of gravity in our lives is pitifully small. Why? Because you're sitting at a pretty large desk right now, and you don't feel gravitationally attracted to that desk. Worse, you don't feel gravitationally attracted to your classmates because of their mass. I mean, can you imagine how awful it would be if all of us felt an irresistible attraction to the most massive person in the room? Ugh, Austin Powers moment. So, Cavendish himself has mass. This means he can't stay in the lab tinkering with the equipment, or his mass will affect the results, and the bowling balls will be attracted to him instead of to each other. So Cavendish paints a grid, kaviyachol, on the wall of his lab, locks the door, and goes outside, illuminates it. Doesn't have lasers in that time, so I'm sorry to say that he used whale oil to provide a straight beam and a constant illumination, and leaves his lab for a week. When he comes back, the torsion balance has twisted through the smallest of small angles. However, thanks to the grid on the wall of the lab, he can stand outside and measure. He knows the angle, he knows the time. A week, convert to seconds. This means he can find the angular acceleration. He knows the moment of inertia of his apparatus because he built it himself. Look, sphere, 2/5 mr squared, another sphere, 2/5 mr squared, bar between them, 1/12 ml squared, and so on and so forth, out of the whole apparatus. If he knows the angular acceleration and he knows the rotational inertia, then he can find the torque. And if he knows the torque and he knows the radius of the apparatus, he can divide out and he can find the force. It is a minusculely small force that Cavendish measures. That's why. Convert this to a form you can use in an equation. Let's say Cavendish's two identical bowling balls are 90 kilograms apiece, and let's say Cavendish places them 2 centimeters apart. Pause, proofread. Do we have enough information to solve for G? Is there anything else we need to know? Pause, think, press play when you've found it. That's right, we need to find the radius of the bowling balls as well, center of mass to center of mass. Whoo, good thing we checked that picture was not to scale. Now, found the radial distance between them? Good. Solve for G, the universal gravitational constant. Press pause, press play to check your work. Proofread. Did you convert all your centimeters to meters? Did you convert all your micronewtons to newtons? Pause. Proofread again. Proofread some more on your calculator. Did you use the double capital E instead of times 10 to the, so that you didn't get typos? Good. Did you get the final numerical answer of 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared? Good. That's it. That is big G. Big G is the universal gravitational constant. This number describes the strength of gravity in the universe. Gravity is the weakest of all known forces in the universe. Look at that 10 to the negative 11th. That's minuscule. That's past nano into pico. Compare how easy it is to lift things with static, aka bad hair day, and magnets. Electricity and magnetism leave gravity in the dust. This is why. The universal gravitational constant describes the strength of gravity in the universe. Now that you've found it, you can use it for as long as you live in this universe. The little green people on Alpha Centauri in their 11th grade physics class, they're using the same universal constant you are. Please note, this capital letter is not the same as lowercase g. Take some notes, sort them out. Lowercase g, 9.8 meters per second squared. Enjoy it while it lasts. It'll be gone in about 2 minutes. This is the acceleration due to gravity on Earth in meters per second squared. This is the universal constant that describes the strength of gravity, not just on Earth, but all over the universe. This is a universal constant. This is a rate of speed change in meters per second going inward toward the surface of the Earth. Do not take this one for granted. This one is always true. Now, find little g. Last semester you assumed it was a constant. You assumed wrong. Little g is short for the acceleration due to gravity. Change notation if it makes you any happier. Acceleration is force over mass. Take the force of gravity from earlier in your slide, plug it in, divide by mass. This is m2, the little mass, the lowercase mass. Pause, simplify, press play to check your work. Got it? There is the acceleration due to gravity. Put a box around it. Now you have it. Find the acceleration of gravity on Earth. Pause. Take a good solid minute to do all your algebra. When you look at your screen and say, oh, then you'll have the right answer. Pause. Ready? Anything familiar? Why isn't it 9.81? Look at the formula. Radius is measured from center of mass to center of mass. Your textbook was published in a place where the radial distance to the center of mass was a little small, and therefore the g was a little high. 9.81 is for this metro area, flatlands, prairie, lakeshore, Chicago, where g is 9.81 meters per second squared. However, if we go to a valley, r will be smaller and g will be bigger, maybe 9.82 or 9.83 like you just calculated. Or if we go here to the Rocky Mountain Hebrew Academy of Denver, the mile-high city, the 11th graders there in their physics class will use a g of 9.79 meters per second squared because they're further from the Earth's center. Pretty cool, huh? Find g on the moon. Press play when you're ready. Watch those kilometers. Proofread. Got a final answer? 1.76 meters per second squared? Yep. Is there gravity on the moon? Yes, there is gravity on the moon. Things just fall at a slower rate on the moon than they do here.